It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good evening, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we are starting nuclear physics, and this lesson is on mass defect and binding energy. Before we get to those, let's just look at some symbols of elements that we learned in chemistry. So, if we have the letter X, that's going to represent our element. In the bottom left corner, the letter Z represents the number of protons. And in the top left corner, the letter A will represent the sum of the protons and neutrons. So number of protons plus neutrons. If we look at your Regents Chemistry reference table, in the top left corner, we have the atomic mass. For this class, we're going to call that the chemical atomic mass, which is the average mass of the isotopes based on differing amounts of neutrons. So why don't we define that as well? So the chemical atomic mass. So that's going to be the average mass of isotopes. And in chemistry, you might call this the atomic mass unit. We're going to continue calling this the universal mass unit. So it's in universal mass units. And that's represented by the letter lowercase u. Now, in this class, we want to know what the specific atomic mass is, and we're going to use Appendix B, and that'll tell us the atomic mass, still in universal mass units, based on the number of neutrons. So rather than the average chemical atomic mass, we're going to look at the specific atomic mass in Appendix B in your textbook. So let's just do a few practice problems. This is practice problem number 1 in your worksheet. And all we want to do is figure out the number of neutrons in any given element. So the first example we have is uranium-234. And we know that there's 234 protons and neutrons. And what we want to do is find the number of neutrons. We'll start with the sum of the protons and neutrons, which is 234. And since we want to find the number of neutrons, we can look up how many protons there are. We'll look at our reference table for uranium. And we see that there are 92 protons. So 234 minus 92 gives us 142 neutrons. Why don't we do one more? Let's do letter C, which is carbon. but in this case it's carbon 15. So we know there are 15 protons and neutrons. We'll look in our reference table for carbon, and we can see that there are 6 protons. So 15 minus 6 gives us 9 neutrons. We previously learned that the mass of the protons, the neutrons, and the electrons, if we add all of those up, it's going to be much less than the mass of the atom. That's because that missing mass is responsible for the binding energy of the nucleus. So that's what we're going to calculate next. But first we need to know the masses of the protons, neutrons, and electrons. The mass of a proton in universal mass units, I guess we'll write proton, is equal to 1.007276 universal mass units. The mass of a neutron is equal to 1.008665 universal mass units. And we also want to know what the mass of the sum of a proton and an electron is. We're going to call that m sub h for hydrogen, which is the mass of a proton and an electron. If we add those two together, we get 1.007825 universal mass units. Let's look at helium and figure out how much missing mass there is in a helium atom. So the first thing we want to do is we'll look up what the mass of a helium atom is. We're going to use Appendix B in our textbook, and we get 4.002603 universal mass units. So if we were able to pluck out a helium atom, put it on a scale, this is what we'd get in universal mass units. We could see that helium is made up of 2 protons and 2 neutrons. So to calculate the mass of the individual particles that make up helium, we have 2 protons, but we're going to use 2 mass of the hydrogen because we're also going to have 2 electrons, so 2m sub h, plus 2 neutrons, and that'll give us the atomic particles that make up the helium atom. So 2 times m sub h, 1.007825 universal mass units, plus 2 times the mass of a neutron, 1.008665 universal mass units. We add those together and we get 4.03298 universal mass units. What we could do next is now calculate how much of that mass of the protons and neutrons and electrons is converted to energy. So let's find the change in mass. So delta M is going to equal the sum of the mass of the hydrogen atoms, or the protons and electrons, plus the mass of the neutrons, minus the mass of helium. So that'll tell us how much of the mass went into energy. So if we do that, we have 4.03298 U's. That's the protons, neutrons, and electrons, minus the mass of helium, 4.002603 U's, and that gives us a mass of 0.030377 universal mass units. So that's how much mass was then converted or used for energy to bind the nucleus. We learned previously how to go from universal mass units to mega electron volts. So why don't we convert the mass to energy? So that's also equal to 0.03077 universal mass units, and we have 931 mega electron volts per 1 universal mass unit. Plug and chug, and we get 28.28 mega electron volts. And that's the binding energy used, the binding energy of a helium nucleus, 28.28 mega electron volts. And that binding energy is due to the change in mass, which we're going to call the mass defect. And that's a result of Einstein's equation, E equals mc squared, where mass and energy are equivalent. We'll write down the formula for mass defect. That's delta M. And that is the sum of the mass, the sum of the mass of the mass of the protons and electrons, which we'll use for hydrogen, plus the sum of the mass of the neutrons, minus the mass of the element that we're given. So that's how we calculate the mass defect. And then the binding energy, all we have to do is convert it to universal mass units. Excuse me. And that's just 931 mega electron volts is equal to 1 universal mass unit. So we could say that it's whatever the mass defect is, delta M, times 931 mega electron volts per 1 U. Let's do another practice problem from your worksheets. And why don't we do number 2B? (2B) asks, what is the binding energy of the following atoms? And for 2B, we're given a tritium atom, which is hydrogen with 1 proton and 2 neutrons. And we're also told the atomic mass of this tritium atom is 3.016049 universal mass units. Again, we could find this in our Appendix B of the college textbook. So to find the binding energy, let's find the mass defect first. That's going to equal the mass of the hydrogen atom. Plus, in this case, we have 2 neutrons. So 2 times the mass of the neutron, minus the mass of the element, we'll call H31. So all we'll do is just plug and chug. We have, for the mass of the hydrogen atom, that's the sum of the protons and 1 proton and electron. 1 proton and 1 electron is 1.007825 U's plus 2 times the mass of the neutron, 1.008665 U's, and then minus the mass of the tritium nucleus, 3.016049 U's. Plug and chug, and we get delta M to equal 0.009115 universal mass units. To convert that to its binding energy, 931 mega electron volts per 1 universal mass unit, and we get 8.49 mega electron volts. And that's it for this video. Thank you for watching, and I hope you found it useful. See ya!